Good evening, everyone. Myself, Ashwin Harrison. I'm gonna present a topic about universal tensile testing machine. Purpose and applications. A universal tensile machine applies a precisely controlled tensile load to a standardized specimen while measuring force and extension. It is used to characterize metals, polymers, and composites for designs and quality control. Running tests to a target strain or to fracture to quantify strength, ductility, and stiffness. UTM types. Electromechanical drive. Motor and screwdriver offer clean, quiet operation with excellent low speed control, common for tensile tests on metals and plastics, up to moderate force, with high displacement resolution and easy lab maintenance. Servo hydraulic drive. Hydraulic power delivers high force and rapid loading, ideal for high strength metals, fatigue, and fracture work needing fast rates or cyclic control. Requires hydraulic setup and careful turning for stability. Pneumatic drive. Compressed air enables simpler low force testing with basic rate control, ideal for thin films, elastomers, or educational setup, prioritizing cost and simplicity but limited in force capacity and precision. Types of test in UTM. Tensile test measures how a material reacts when pulled apart until it breaks. Compression test evaluates how a material resists crushing or compacting forces. Adhesion test evaluates the bond strength between layers or adhesive. Pull out test, spring test, peel test, peel test and adhesive sensor both evaluates the bond strength between layers or adhesives. Components of UTM. Load frame, the structural body housing the specimen. Load cell, a sensor that measures the applied force with the high precision. Cross head, the moving part that applies the force. Measuring scale, it used to measure the scale of the material. Output device, where the output is shown from the device. Test fixtures, interchangeable attachments used to secure the material based on the test type. Example, tensile jaws, compression platens. Block diagram of a single column UTM. Compact bench mounted frame with one vertical support. Generally, it is limited up to a low force testing, typically up to 5 kilonewtons or 500 kgs. The moving stock where it moves vertically and the material kept under the load cell and it starts to move vertically to compress the material and starts to compress it and shows the strength of the material. Block diagram of a dual column UTM. A robust arch frame structure with two vertical columns for increased stability, suitable for medium to high force testing up to 600 kN or more. Key components: mechanical and sensing. The load frame and moving crosshead ensure stable aligned motion while grips hold the specimen securely. A calibrated load cell measures force and a extensometer directly measures strain, enhancing accuracy for modulus and yield analysis over crosshead travel. Control and a data system. The controller sets test modes, load, displacement or strain, speed and limits sensing sensors. Software records force extensions or strain data, applies ASTM, ISO calculations and output plots and key values with the metadata for traceability and repeatability. Stress strain elasticity. 30% represents the early recoverable information used to compute Young's modulus from the slope, assuming proper strain measurement and alignment. Yield 25% represents the transition where permanent strain begins. It is commonly found by a 0.2% offset method when no clear yield point appears. UTS 25% represents the rise to ultimate tensile strength and the start of nicking, where engineering stress peaks while true stress may still increase. Break 20% represent the final drop to fracture. Students relate the break location and a reduction in area ductility, defects, and gripping effects. Test outputs. From stress strain data, yield strength 30% marks the onset of plastic flow, while ultimate tensile strength of 30% is the peak stress before nicking. Elongation at break 20% captures ductility to failure and Young's modulus to 20%. is the initial slope that quantifies stiffness. All are computed from force extension converted to stress strain. The universal testing machines should emphasize their versatility, precision, and a critical role in modern material science and industry. Indispensable versatility. The universal nature of the machine allows it to replace multiple single function testers by simply swapping grips and fixtures. It can perform tensile, compression, bending, and shear tests on a single frame. Guarantor of safety and quality, UTMs are essentially for verifying that materials meet strict regulatory standards, ASM Internationals, ISO DIN, ensuring the structural integrity of everything from aircraft wings to medical implants. They allow engineers to simulate real world stress conditions, facilitating the development of advanced new materials like high performance composites and alloys. While the initial investment may be high, IUTM is cost effective long term by reducing material waste, preventing expensive product recalls, and consolidating testing equipments into one system. Modern digital and server controlled UTMs provide highly accurate, repeatable data through advanced sensors and software, eliminating human error in calculating properties like yield strength and Young modulus. Beyond quality controls, UTMs are critical for identifying the root causes of material failure, allowing for design improvements that prevent future structural collapses or accidents. UTMs have evolved from simple manual apparatus into sophisticated computerized systems capable of high precision data acquisition and integration with advanced manufacturing workflows. In elastic region, the machine measures the a UTM operates on a fundamental mechanical laws to operate a material properties. Hooke's law. In an elastic region, the machine measures the linear relationship between stress, force per unit area, and strain deformation, helping calculate the modulus of elasticity. The machine maintains an equilibrium of forces between the applied load from the actuator and the resistance from the specimen to ensure precise measurements. Modern UTMs are servo motors and digital controllers to continuously monitor and adjust the crosshead speed or force in real time, ensuring highly consistent test conditions. To extend its universal capabilities, specialized attachments are used. These precision instruments attach directly to the specimen to measure minute changes in length, providing far more accurate strain data than crosshead movement alone. These units surround the specimen to perform tests at extreme temperature ranging from minus 70 degrees C to 1280 degrees C or specific humidity levels, stimulating real world operating environments. Beyond standard jaws, UTMs use pneumatic grips for their thin films, wedge grips for high strength metals, and bolted fixtures for metal components. Generates live stress strain curves, allowing operators to visualize yielding and fracture as they happen. Instantly computes complex values like 0.2% offset yield strength, ultimate sensor strength, and elongation at break. Modern system can export data directly to laboratory information management system, LIMS, or quality database for enterprise-wide tracking. Essential to verify that the load cell and displacement sensors are within specified tolerance, typically plus my 0.5% to 1%. Standard practice like ASTM EF4 require recalibration whenever a machine is moved to a new location. Includes lubrication of lead screws, checking electrical connections, and inspecting grip teeth for wear to prevent specimen slippage. With this, I conclude my presentation. Thank you.